Hello, everybody. I'm Connor Westcott. Didn't want to do that. Go back. Oh, I'm Connor Westcott. I'm a master's student of computer science at the University of Central Florida, working at the Florida Space Institute with Dr. Julie Brisset. Today, I'm going to talk about a research project I've been working on for the past few months, which is an updated model for extracting water volatiles out of permanently shattered regions on the moon, which I effectively call TWEM. So first off, what is it? So the idea is we're going to thermally extract water ice from the lunar surface. Why we want to do this? Well, it's kind of the easiest and most straightforward way that we could think of. You know, if it's easy, let's try it, see if it works, compared to either shipping it out from Earth to the moon or melting the regolith and doing electrolysis with it. To do this, it is a 3D FEM simulation in the ever modern Fortran 90. Where we simulate a 1.2 meter square surface area with a 1 meter depth of icy regolith. So to do that, we need to model it. So the first part is the three main things of thermal water extraction. Thermal, we have to diffuse any kind of heating that we do. To do this, we use the Crank-Nicholson method for 3 dimensions. Then we have to figure out how we're going to change the state of the water. So to this, we use the Arden-Buck equation to determine if we need to either go from a solid water or to a vapor. Once we have it in the vapor, we need to figure out how to get it from within the regolith to no longer being within the regolith. So to help with that, we use Darcy's law for gas motion with the assumption of laminar flow, because the simulation's resolution is very small. Gas typically won't flow more than a 5 centimeter distance. So we make it easier on ourselves and just kind of stick with some laminar flow assumptions. Then from there, this is the previous work that Dr. Brisset et al. Had worked on, where they implemented those kind of 3 main thermal water extraction properties with a very static regolith description. And here we see that for lower wattage powers that we don't really produce much, and that isn't until we get into very high 10⁴ watting that we actually can produce over a kilogram of water. So to help increase this and make it more realistic, I have implemented some more dynamics into regolith stuff. So first off is the regolith emissivity, and it appears that when I translated this to a PDF, it ate some of my equations. So first, for the emissivity, originally they just had a static value of 1, but that's not necessarily how it works. So we've updated it using Cloy's analysis of the JSC1AF simulant to kind of have a fitted equation to determine the emissivity of the surface as the temperature increases. And here we can see in this graph over on the far end that the emissivity can change the starting production time from heating either through surface or with drills. But at the end, the overall production is not terribly affected. And this is because, as we can see in the graph, as we start increasing the temperatures, we start approaching the value of 1. And because, especially with higher wattages of heating, we more rapidly approach those temperatures and stay at a constant value of close to 1 for longer. Next up is porosity. Originally, this was a value of 0.3. And we updated this to use the Vasavada et al.'s research for rock density. And here we can see that it really didn't have too much effect. And this is because the Vasavada equation is very rapidly approaching the value of 0.3 for our depth of no more than 1 meter. So there's not too much difference in production times or quantity that we find in dynamic porosity. Next up is permeability. Originally, we took the value that was for just sandstone because that was what we could just find at the time when originally creating the model. But fortunately, Westcott et al. Last year had published a paper studying very similar to this in actual lab environments of trying to heat up regolith in a icy and lunar condition, and refined an equation for permeability that takes not only into account the regolith, but the ice within it, which actually impacts quite a bit, as we can see here, where productions are severely suppressed and severely delayed in the time it takes. The last thing we updated was the thermal conductivity. Originally, this was just the average between the regolith and the water ice that was present, which generally came around to be 0.7. But I went ahead and implemented the Rice equations for regolith thermal conductivity, which takes into account the thermal conductivity of water ice and the thermal conductivity of regolith. And within the regolith, it looks at 4 key components: the grain-to-grain interactions of the regolith, the gas between the grains, the gas interacting with the grains, and any kind of radiative emissive properties that the grains may have. And here we can see that it has a generally noticeable impact where productions are often delayed and can either be significantly more or significantly less than just a static thermal conductivity. And this is really because of, as we change from a solid to a gas in water ice, the thermal conductivity significantly changes because the thermal conductivity of a gas is very different than the thermal conductivity of water ice. So here, looking at kind of the final results we got of extraction yields, where we find how much ice did we start with and how much did we end up with in terms of water collection. And here we see for low powers of about 100 watts, more drills is better. But it depends too, because the amount of ice presence, if it's a ice poor regolith or an ice rich regolith, can impact, as there's some slight dips and troughs in there, but they get exacerbated even further as we increase the temperature, where surface starts to become a more effective style of heating for all types of ice. But the ice can start having a crossing over point where less ice is actually a little bit more effective than more ice until you get to the most amount of drills. Lastly, at 10,000 watts, which is a lot, but we see fantastic yields, especially for surface, where at 10% of ice, very ice-rich regolith, we see near 80% or 88% of the water that was in the regolith being extracted for use. But another thing that's interesting is that, unlike the medium of 1,000 watts, that more drills starts to become better again, but there is some diminishing returns and ice poor because there's just not enough ice. We've extracted all of it, and more power just kind of makes it go quicker. But here is a look at kind of how the simulation sees it and why we see some of these yields. Here for the surface heating, all the ice has been turned into either a vapor or extracted, nearly down to the last 2 layers of our simulation resolution. And those last 2 layers are about 5%, which we expect because that's what we started with, but every layer above it is nearly gone. But with the most amount of drills at 25, we see a sudden spike around the edges where we're now almost at 15% ice concentration, because those regions are so cold because the drills can't permeate enough heat through the system, as well as the drills only go about halfway through the entire regolith depth. So we miss out on a lot of ice on the underneath, which also impacts the effectiveness of all of this. Thank you. So with conclusion, it's a little bit of a mixed bag, but the heating method really depends on ice content and how much power you have. You know, ice pours typically favor more drills, as well as, but higher powers tend to favor more surface. As you see, we can penetrate further with the heat. As well as a big issue going forward is going to be refreezing. You know, with those drills, we're losing a lot of ice to refreezing in such high concentrations. You know, how are we going to be able to prevent that? But surface kind of alleviates that because it evenly spreads the heat out across the entire system. So with that, thank you for your time.